Hello, this will be a demonstration of proposition 12 from book 2 of Euclid's Elements, which states that in obtuse angled triangles, the square on the side opposite the obtuse angle is greater than the sum of the squares on the sides about the obtuse angle by twice the rectangle contained by one of the sides about the obtuse angle, namely that side on which the perpendicular falls and the straight line cut off outside by the perpendicular towards the acute angle. This makes no sense if I don't draw it out, so I shall draw the given. We are given the obtuse angle triangle ABC such that the angle BAC is an obtuse angle. That's that angle right there. We're also going to produce CA to some point D, and furthermore, we're going to, through point B, make a straight line BD perpendicular to DC, like that. So that's our construction. And we're going to say that the straight line on the side opposite the obtuse angle, in this case that's BC, so BC squared is going to be greater than BA squared plus AC squared, those are the sides about the obtuse angle, is going to be greater than those two squares by twice the rectangle contained by CA and AD. How does this given fit? How does this specification fit into our enunciation? Well, CA is one of the sides containing the obtuse angle, right there. So we have the obtuse angle right there, and CA is containing it. And it is that side on which the perpendicular falls. The perpendicular you can think of as just the height of the obtuse angle triangle. And so the height is going to be at right angles with the base. So we can think of AC as the base, and the perpendicular is the height perpendicular to the base. And AD is the straight line cut off outside by the perpendicular towards the acute angle. So AD is outside the original triangle BAC. So that's where that fits in, and it's cut off by the perpendicular. So if we produce CA indefinitely in that direction, AD is where the height from B cuts it off. And so we're going to prove that BC squared is greater than BA squared plus AC squared by twice the rectangle contained by CA and AD. First, by proposition 4, because the straight line DC has been cut randomly at point A, we can say that the square on the whole, DC squared, equals the squares on the segments, that is CA squared and AD squared, plus twice the rectangle contained by the segments, that's twice the rectangle, CA times AD. And because this is true, we can add the same thing to both of them, namely BD squared, so that we can say that CD squared plus BD squared equals CA squared plus AD squared plus twice the rectangle contained by CA and AD plus BD squared. This is proposition 2.4, and then the second part of it, where we simply add equals to equals, that's proposition, common notion 2, simply adding equals to equals. Next, we know that because the angle at D is a right angle, we can say that BC squared equals CD squared plus BD squared. That's proposition 147. So we're dealing with the right angle triangle BDC. And so we can say that the side subtending the right angle, BC squared, the square on that is going to equal the squares on the sides containing the right angle. So we can say that BC squared is going to equal BD squared plus DC squared. And so we can substitute the CD squared plus BD squared on this side of the equality for simply BC squared. And we can say that BC squared equals CA squared plus AD squared plus twice the rectangle, CA times AD plus BD squared. Similarly, that is also because of proposition 147, in the right angled triangle BAD, we know that BA squared is going to equal BD squared plus AD squared. And so we can take the AD squared and the BD squared right here and simply combine them into a AB squared, so that we can say that BC squared is equal to BA squared plus AC squared plus twice the rectangle CA times AD. What further follows from this is that BC squared is greater than the sum of the two squares on their own, and it is greater by twice the rectangle CA times AD. This being what was set out to have been proven, we are done with the proposition, therefore, etc., QED. Now, the really neat thing about this proposition is that it is one form of the law of cosines. We saw one form of it in simply the Pythagorean theorem, where the angle is a right angle, and in 2.12 we deal with the case where the triangle has an obtuse angle. So how exactly does this work out to be the law of cosines? Well, let's work it out. We're going to draw. Actually, I'm not going to do that. I'm going to just work with this triangle right here, the triangle that I've already drawn. I was going to recreate it, but I don't think I'm doing that. Okay, so we know that from this proposition that BC squared equals AB squared plus AC squared plus twice, I'm not even going to draw the rectangle here, I'm simply going to draw AC times AD. Now, the whole of the connection between this proposition and the law of cosines hinges on what the side AD is in relation to all the sides and angles that we already know. So let's look at this triangle. By proposition 113, we can say that angle BAC plus angle BAD equals two right angles. You can say that by prop 113, right? And so if we subtract BAC on both sides, we can say that the angle BAD equals two right angles minus the angle BAC. That's just common motion 3. Okay? Now, excuse me. Now, if we take the cosine of this angle BAD, actually, I'm going to, so if we take the cosine of angle BAD, well, the cosine is adjacent over hypotenuse, so the adjacent to angle BAD is AD, and the hypotenuse here being AB, so that the cosine of the angle BAD is AD over AB. Now, we just saw that we can express the angle BAD as two right angles minus BAC, so let's do that. Cosine of two right angles minus BAC equals AD over AD. Now, this is a common trig identity. We can say that the cosine of two right angles minus any angle equals the negative cosine of simply that angle. And so we can say that the negative cosine of angle BAC equals AD over AB. And so then if we multiply AB on both sides, we can say that AD is equal to the negative of AB cosine angle BAC. So let's take our original equation and substitute that in for AD, so that we can say that BC squared equals AB squared plus AC squared. Substituting this in, we're going to say minus twice AC times AB times the cosine of angle BAC. Now, putting this in only algebraic terms, as it is usually said, we're going to say that BC is A, BA is C. We're going to say AC is B. We're going to keep the angles the same. It's common practice to label sides as the lowercase of whatever angle they are subtending, so that we can say that A squared equals B squared plus C squared, I'm going to swap those two, minus 2 BC cosine, well, BAC is simply A. And this is a common way in which the law of cosines is written. And so we have shown sufficiently that proposition 212 is an example of the law of cosines, namely where the angle inside the cosine is an obtuse angle. In the next proposition 213, we shall see the law of cosines where the angle inside the cosine is an acute angle. And having nothing more to say about this proposition, I will move on to 213.